Hello and good afternoon, everyone. I am Hrushikesh Varma, a PhD student at University of Florida. Firstly, I'd like to apologize for not being able to attend the conference in person, and also thank the organizing team for arranging this. Today, I'll be presenting our work, EMI-LiDAR, uncovering vulnerabilities of LiDAR sensors in autonomous driving setting using electromagnetic interference. This research project is a collaboration between the Cyber-Physical Systems Security Lab at the University of Florida and the University of Electrocommunications in Tokyo. Jumping right into it. In this work, we discover a new vulnerability in LiDAR sensor used in autonomous vehicles for object detection. We show that the LiDAR sensor data can be maliciously altered using electromagnetic interference, forcing object detection and fusion models used in autonomous vehicles to misdetect, misclassify, and even see fake obstacles in front of the vehicle. We investigate the existing defense methods, such as denoising and subsampling techniques, and show that they only improve the model performance by 8%. Then we model and evaluate two novel injection detection methods. Now, before we go into the details of this vulnerability, let's look at what a LiDAR sensor is, how it works, and how it is used in autonomous vehicles. LiDAR, short for light detection and ranging sensors, use time-of-flight mechanisms to estimate the depth information of the surrounding obstacles. Although there are various types of LiDAR sensors, we focus on LiDARs that use time-of-flight circuits. To perceive depth, LiDAR sensors first fire one or multiple laser pulses. These pulses, when intercepted by the obstacle, are reflected back to the LiDAR. These reflected pulses are called echoes. These echoes are received by the photodiodes present in the LiDAR receiving circuits. The LiDAR then measures the time taken by the pulses to return back, and since the speed of light is always constant, it uses this information to estimate the depth of the corresponding object, hence the name time of flight. This work focuses on spinning LiDARs, which generally consist of a spinning motor that allow multiple lasers and photodiodes to rotate, firing and receiving information from all around, thus collecting depth in all directions. The horizontal angle covered by the LiDAR is known as the field of view of the LiDAR. Spinning LiDARs generally consist of a 360-degree field of view. The resulting collection of these raw signals is called a point cloud, where each received echo is a point in 3D map with its own geometric coordinates. Autonomous vehicles uses the data that it collects from the LiDAR, camera, and other sensors in its autonomous driving framework to perform automatic operations such as obstacle avoidance. The autonomous driving framework typically consists of four main components: the perception, the localization, the planning, and the control modules. Perception in particular refers to the ability of the autonomous vehicle to collect and process relevant information from the surrounding environment to perform navigation and control. These perception components implement ML-based object detection models to detect obstacles such as other vehicles and pedestrians in the trajectory to help itself navigate. Previous works have demonstrated that LiDAR-based object detection models are vulnerable to signal injection attacks. Using adversarial machine learning or other software vulnerabilities, these works show that LiDAR-based object detection can be fooled to perceive fake obstacles or not detect existing ones by strategically injecting point clouds at specific locations by shining laser beams precisely synchronized with the LiDAR rotation. These works follow the same attack methodology not only against LiDAR-based detection, but also fusion-based detection models. However, such attacks are difficult to pursue since they require the attacker to precisely synchronize with the victim LiDAR and also requires accurate aiming at moving vehicles. In our research, we discovered that electromagnetic waves induce voltage changes on electrical circuits, which appear as perturbations in the resulting point cloud of the LiDAR. The circuit's susceptibility to this electromagnetic waves depend on the injected signal and its frequency. The resulting perturbations in the LiDAR point cloud show different but regular noise patterns, such as the ones shown in this picture. For example, in a VLP-16 LiDAR, we observe two types of 3D patterns, a sinusoidal pattern and a random pattern found at injecting electromagnetic signal of different frequencies. We call these point cloud noise as sinusoidal perturbation and the random perturbation. Motivated by this finding, in this work, we investigate the impact of intentional electromagnetic interference on LiDAR sensors to answer the questions as depicted in this slide. Overall, we investigate the impact of interference on LiDAR sensors and consequently on autonomous vehicles, and try to find out what are some potential ways to defend against them. We consider the following threat model for our analysis. The attacker goal is to affect a specific region of the LiDAR field of view, to induce misclassification or misdetection of one or more obstacles already present in the field of view, or even create non-existing obstacles. We assume that the attacker setup is placed in proximity of the victim car, for example, on side of a road or near to an intersection. For safety reasons, we only conducted proximity experiments with the transmitted antenna a few centimeters away from the victim LiDAR. We modeled the perturbations to estimate the transmitted power required for longer distances. As defined in our research question, we first study how electromagnetic interference impacts the sensing mechanisms of the time-of-flight circuits in the LiDAR sensors. We first conduct an empirical test on a VLP-16 LiDAR and notice that at increasing transmitted power, even without the presence of an obstacle, the EMI generates point clouds in an area, as you can see in this picture. Since the transmitted laser pulses never return, we conclude that the receiver part of the time-of-flight circuits in the LiDAR are significantly susceptible to the EMI waves. To demonstrate that, we perform electromagnetic injection using a floating probe at different locations on an off-the-shelf photodiode, which uses a time-of-flight circuit. As you can see, the measured average output voltage for the circuit generated by this injection is highest when the probe is closer to the amplifiers, suggesting that they're the ones most significantly impacted. Once found the probable cause of this susceptibility, we investigate how the various perturbations or the patterns that we have seen in the point cloud previously are generated. The LiDAR digitalizes the output of the amplifier using an ADC. According to the Nyquist-Shannon theorem, to accurately represent a signal, our sampling rate must be at least twice the maximum frequency of the signal. However, the LiDAR ADC collects up to 500 million samples per second, and the sampling is further limited by the spinning and multiplexing of the photodiodes. As you can see, in this figure, we injected a sine wave with approximately 960 megahertz on the VLP-16, and by shifting the injection frequency at 200 hertz of increments, we are able to receive multiple perturbations and create multiple perturbations, including the sinusoidal and random perturbations that we saw before. To exploit this vulnerability, an adversary can consider to affect a specific region in the LiDAR field of view or a horizontal angle. This control can be achieved by synchronizing the LiDAR with the transmitter EMI, similar to the laser injection attacks that we saw previously. Then the adversary can inject a simple sine wave using a radio transmitter and an amplifier. Moreover, the adversary can control the output gain of the EMI transmission, which is linearly proportional to the output transmission power. We empirically define the attacker capability by first determining the minimum horizontal angle that can be affected by our attack. We observe that it is 3 degrees due to our hardware setup limitations. We characterize the random perturbation based on the mean point displacement at increasing injection power, and the sinusoidal perturbation based on the amplitude. For both perturbations, we observe that the pattern amplitude increases along the horizontal plane, indicating change in the distance calculation, topping at 25 dB gain, which is equivalent to 2 watts of injection power. To study the effect of these perturbations on autonomous vehicle object detection models, we synthesize these perturbations that we measured on the VLP-16 LiDAR, and we analytically model the relationship between the transmission power and the perturbations that we see. We model the random perturbation based on the mean and standard deviation, and the sinusoidal pattern based on the amplitude and wavelength of the perturbations we see in the 3D space. We then apply our model perturbation to the Kitty dataset to simulate the attack. Then we evaluate the impact of the transmitted injection power and the horizontal angle on 3 different LiDAR-based object detection models: point pillars, point RCNN, and Bido-Apollo CNN segmentation, all 3 of them trained on the Kitty dataset. And we evaluate based on the object detection and classification rates. We consider 2 modes of analysis: the worst case IOU, where we consider that an object is detected if the intersection over union is greater than 0 with respect to the ground truth, and the default case IOU, where we consider the default intersection over union values considered in the corresponding works. As you can see, the object detection rate drops to below 50% for pedestrian and cyclist objects in all models, and to below 60% for car objects with the sinusoidal perturbations. The point RCNN model is more robust to geometric variations of the point cloud data. We hypothesize that this is the reason for the smaller drop in classification rates when compared to point pillars, which is a voxel-based architecture. We then evaluate the impact of the horizontal angle. For the object detection models, the results show a sudden drop in object detection with just 3-degree attack angle, indicating that even small horizontal angles can significantly impact the object detection. In both the models, the detection rates do not drop any further at larger angles. We hypothesize that this is because at large angles, the perturbation already covers the entire obstacle, and increasing the horizontal angle any further would only impact the object detection in very small. For the segmentation model, we observe that an 18% drop with just 4-degree of attack angle with the sinusoidal perturbation. The segmentation models annotate the scene point by point, giving more granular information about the scene. This makes the segmentation models more susceptible to the EMI perturbation. As a result, we can see that the object detection is impacted even at large horizontal angles. For the WIOU case, we see that the object detection rate in the detection models drops below 50% at 3-degree attack angle and below 50% with 8-degree attack angle in the case of the segmentation model. We then evaluate the impact of these perturbations on two camera LiDAR fusion models, AWOT and Frostrom-Conrad. For the AWOT, the perturbation drops the object detection rate below 50% for pedestrian and cyclist object classes, and for pedestrian and car object classes in the case of Frostrom-Conrad. The classification rate drops further below for AWOT, but we do not see any further drop of classification rates in Frostrom-Conrad. This happens because in Frostrom-Conrad, the region proposals created by the model for object detection come from the camera image, which is not perturbated by our injection in any way. We further conduct a proof of concept experiment in real-world scenario on the VLP16 LiDAR. We test the impact of the perturbation on a pedestrian object using PFINet by placing the pedestrian at 2, 4, and 6 meters from the target victim LiDAR. We limit the gain to 25 dB for safety constraints. We evaluate the impact of perturbation based on the intersection over union between the detected bounding box and the actual bounding box, which was manually labeled. The results show that at 2-meter target pedestrian distance, the intersection over union drops below 50% for only 2 and 14 dB gains, corresponding to 200 milliwatts and 1.1 watts of injection power in random and sine signal injection, respectively. For 4 and 6 meters, we see that the average intersection over union drops from 38 and 43% to 22% at a 25 dB gain. Finally, we study the fake object creation by perturbing the signal at 70 dB gain. We observe that the perturbations create up to 8 false positives per frame and up to 4 false positives per frame in point pillars and point RCNN, respectively. These results show the fake object detection with sinusoidal perturbations. Although the perturbations create additional fake obstacles, the total drop in precision is still low because the fake obstacles do not correlate with the false positives that are already present in the model without any attack. However, this amount is already enough to cause certain models to drop below the random guess. In the real world, we see a 20% drop in both precision and recall rates. One possible way to mitigate this injection is to reconstruct the original point cloud using denoising models. We implemented score-based denoising and observed that it is insufficient to reconstruct the point cloud perturbed by the interference. To improve the denoising results, we perform adversarial training of the score-based model using the perturbations that are generated by the electromagnetic interference and show that they only improve the classification by 7% and the object detection by 6% on the KT dataset. Another way is using 3 points of sampling to improve the robustness against noisy data and adversarial attacks. However, since the EMI injection perturbs all the points in the affected region, it reduces the effectiveness of subsampling. We show that the point cloud subsampling increases the object detection by 8% in the best case scenario and only deteriorates the performance in the other cases. Thus, we propose two detection methods based on the observed perturbations. LiDAR ground point filtering in AV perception system discards the ground points in the LiDAR field of view outside of the region of interest. Since the EMI perturbations affect the entire point cloud, it also perturbs the ground points in that region. Our methodology extracts the ground points of this LiDAR scene and analyzes them to detect EMI injection. We do so by calculating the signal to noise ratio and trying to find out the peak in those values. We observe a 94% true negative rate and a 98% true positive rate. In addition, our analysis shows that at high gain values, the average intensity of the points in the region affected by the perturbation dropped by almost 5 times. Thus, a faster and a simpler alternative defense can leverage this factor to detect potential injection. Using this method, we achieve a 100% true negative rate and a 100% true positive rate. Although our proof of concept analysis is based on spinning time-of-flight 3D LiDAR, our experiments show that the vulnerability affects the receiving part of the time-of-flight circuit. We thus believe that the LiDARs that use the same basic functioning as spinning LiDAR, although are still impacted by this perturbation, although the specific characteristics of the vulnerability might depend on the LiDAR. Another limitation is that we only study and characterize the perturbation on one 2D and one 3D LiDAR, while the vulnerability can be generalized across spinning LiDARs with time-of-flight functioning. Also, our setup is limited to static scenarios where the victim LiDAR is stationary, and we have not evaluated end-to-end real-world autonomous vehicles. We leave that as future work. However, our preliminary analysis demonstrates the severity of the threat to the time-of-flight circuits, demanding more future investigations. In conclusion, our work identifies a new class of LiDAR sensor and time-of-flight circuit vulnerabilities, resulting in manipulation of object detection algorithms used in autonomous vehicles. We evaluate and demonstrate the effectiveness of the induced perturbations using electromagnetic injections against two object detection models, one industry-grade segmentation model, and two fusion models. While it is clear that the EMI injection can cause reception and fusion models to fail, it is not clear the extent of this threat over autonomous vehicle technology. In this work, we begin to characterize this threat to understand how better address it. I thank you very much for your time. For more details, please check our paper and visit our website, and I'm happy to answer your questions now.
What do you see as the next major threat against LiDAR? So EMI.
I'm sorry, I can't hear anything.
Sorry, my mic was muted. What do you see as the next major threat with EMI with regards to other sensors in autonomous driving? So LiDAR is clearly particularly susceptible. Is there anything else that's a particular concern based on your investigations?
So I think the threat is more on the component level than on the sensor level. So this threat, this vulnerability is identified in the amplifier, it means that it's highly likely that all the sensors that use a similar mechanism that of amplifier and ADC are likely potentially can be affected by this kind of threat, which means that almost all the sensors are likely to be impacted by this kind of threat.
All righty. Thanks, Hrush. If you have any more questions, then Hrush will be available through his email here, and I'm sure he'll be happy to chat further. Okay, thanks again for a great talk.
Thank you.
And